Good morning, students. I am Magesh Kumar, faculty from Chemical Department of SRM IST. Today we are going to discuss a problem which is used to find the rate equation for a chemical reaction. So to find the rate equation, because rate equation finding is very important, the complete rate equation is necessary to find the design variables for a chemical reactor also. So any performance equation of a chemical reactor will have the rate equation term. So we need the data from experiment, mainly the kinetic data from experiment to find the kinetic parameters such as rate constant and then reaction order. Now to explain the procedure for calculating the kinetic parameters out of the data, see, let us to work out a problem here. Now this problem statement is given here. Actually this problem is using a batch reactor. This collection of data is done with the help of a batch reactor. So using the reactant is a pure gaseous A reactant. Now the data, since it's a gas phase reactant, the data taken here is between time and partial pressure of the component A. So for different time values, the partial pressure of the component or the reactant A is measured. Now that is reported as the data here in this table column. Now let us to use this data to find the reaction order as well as the rate constant for this reaction. Now the stoichiometry of this decomposition reaction is given as A giving 2.5 R. So the stoichiometry equation is given. So it is a decomposition reaction. 1 mole of A is giving us 2.5 moles of R. Now what we need to find is rate equation. So rate equation contains the two parameters. So K and N. So these two parameter values we need to find now with the help of this data. Right? Now solution, if we see the data means then we find that there is a clue given. That is what type of reaction we are dealing here with. For example, from data we observe that at T is equal to infinity, that is after a longer reaction time also. So there is some partial pressure of A is obtained. So that means the component A is still there even after infinite time value also. That means the reaction is not completing within finite time. So even at infinite time also we have some residual component of A that is left out in the reactor. So the reaction is not getting completed within a finite time. Now that means that at T is equal to infinity, partial pressure of A is remaining. This means that the reaction is not completed and considered as a reversible type reaction. So we can consider the reaction to be as a reversible type reaction. Like A giving the component R, and in the same manner the component R also will be giving us the component A. That type of stoichiometry we can consider. Now if you consider that type of reversible type reaction means then see, reversible type means we can have any order also. So for this case, let us to assume that it is a first order reversible type reaction. So assume that a first order reversible reaction. So for first order reversible type reaction, this is the rate equation in integral form. This equation is the rate equation in integral form. So minus logarithm of 1 minus XA by XAE is equal to m plus 1. So that the K volatility some terms are there. Already we have learned this equation. So how to, what are the variables that are there in the equation, everything already we have learned in the previous classes. Now this XA correspond to the conversion of component A. This XAE correspond to the conversion at equilibrium, because the reversible reaction will reach a condition called as equilibrium. So that XAE correspond to the conversion of A, that is obtained at equilibrium. Like that here we have something called as M. This M is nothing but ratio of the initial concentration. Okay, that M is equal to, we can see here that M is equal to CR0 divided by CA0. CR0 is the initial concentration of component R and CA0 is the initial concentration of component A also. But in the problem statement it is given that we are using the pure component A. That means there is no R present in the field. So we can consider the concentration of R to be equal to 0. Since we use the pure component A. So pure A is used. So pure A is used for the reaction. That means M value is equal to 0. So substitute the value of m in place of this in the previous equation. Now this equation it simplifies like this: minus ln 1 minus xa by xae is equal to these two terms. Now it is becoming as 0. M is 0. This m is also equal to 0. So whatever the terms that is left out. So with that the equation is rewritten like this. That is called as equation number 1. Now since we are assuming that it is a first order reversible type reaction, see we would like to test the data. Whatever data that is available or that is given in the problem statement, we would like to test the data with the help of this equation. We are trying to fit this data in this equation. For that, we want the value of xa and xae. So how to find xa and xae value? I think let us to go back to our basic equations under in CRE. We know xa is equal to ca0 minus ca divided by ca0, fractional conversion value. Nothing but the amount converted divided by initial amount, or number of moles of A converted divided by initial number of moles of A. This ratio is called as the fractional conversion. Now this Ca0 and Ca value can be replaced with the help of partial pressure also, by assuming that the applicability of ideal gas law equation, the concentration terms are replaced with pressure terms. That's what we know, that this Ca0 is equal to Pa0 divided by RT. Like that, the Ca is equal to Pa divided by RT. Substitute the values in that equation and replace it with the help of the partial pressure. Now this Xa, it is becoming as Pa0 minus Pa divided by Pa0. Now we know what is the meaning of this Pa0. Pa0 is nothing but initial partial pressure of component A, that is at time t equal to 0. So there is a data available here. You can see here that from the table, at time t equal to 0, the partial pressure value is given as 760. So this is supposed to be the Pa0 value. Right? Now that value substitute here, 760 minus Pa divided by 760. Let it be called as equation number 2. Now we got Xa in terms of Pa. Like that, how to find Xae? Xae is equal to similar formula we have to use. Ca0 minus Ca divided by Ca0. In terms of pressure also, Pa0 minus Pa divided by Pa0. But for this case, we know what is the value of Pa0 at time t equal to 0. This PAE is nothing but the partial pressure at t is equal to infinity. So partial pressure at t is equal to infinity. That is also a data given in the table. So when t is equal to infinity, whatever the pressure value we are given, that is to be taken as the partial pressure at infinity. That is at equilibrium. Partial pressure value at equilibrium. Now when t is equal to infinity, the partial pressure value is also given. That is to be taken as the partial pressure at the condition of equilibrium. Now these values are available, both values are available. Substitute them here and we get a constant value for the Xae. So that value is nothing but 0.8. 80% conversion is the conversion attained at equilibrium. Now substituting this 2 and 3 in equation 1. That is, this Xa value is replaced with the equation 2, then Xae value is replaced with this equation 3. 0.8 is the value for Xae. Substituting them, equation 1 now it becomes like this. This equation 1, now it modifies like this. So minus ln Pa minus 152. See, we are getting some expression which is having which is having the partial pressure in terms of time, reaction time. Now see, we have two variables here now. One is the Pa, other is the time. So we need to plot a graph. Actually this equation resembles like y equal to mx form. Y equal to mx form means nothing but straight line passing through origin with slope is equal to this k1 divided by 0.8. So we are going to consider the partial pressure term as the y variable and t as the x variable, and we would like to plot a graph between these two variables. Suppose if we get a straight line passing through origin, then our assumption is correct. We assume that order is first order. So if the data is fitting the first order equation, then definitely we have to get a straight line passing through origin. Instead of a line, if we get a curve, then the assumption is wrong. So we have to assume some other order for the reaction. So this is the way how the problem has to be worked out. We are testing with the first order kinetics now. So for that, this entire logarithmic term is taken along the y-axis versus t along the x-axis. So this problem can be the testing of the data. I mean, with this equation, it can be done by two methods, either by graphical method, otherwise we can check the consistency of slope also. So we have two different approaches here. One thing is either we have to plot the graph and see that whether we get a straight line passing through origin or not. That is one way. Otherwise we can test the the concordant value for or consistent value for the slope. Suppose if the data is yielding or if it is giving us a straight line means then slope should be same. So we have to use the property of a straight line. So for a straight line, slope should be constant. So we like to use the property also. Either way you can go, either way we can work it out, plot the graph. Otherwise from this equation 4, so K1 is equal to function of PA. I have taken this entire logarithm term to be called as function of PA. So function of PA into 0.8 divided by T. So we need to check whether we are getting concordant value for K or consistent value for K at all data points. If you get like that, then our assumed order is correct. So either way we can either go by graphical method or by this checking the concordant value for the K, that is the rate constant value. Now here I done the problem with the help of the second approach, that is checking the consistency of the K value. So these two things are the given data, P versus PA, they are the given data for us. Okay. Then we need to find the function of PA. Function of PA means this logarithmic term. So when PA is equal to 760, substitute this value here and find what is the value of this function. This function is supposed to be called as function of PA. That value is reported here as 0. Then when PA is equal to 600, substitute this value here and evaluate the function value. That value is 0.30538. Like that we have to calculate the function value at all PA values. That is reported here in this third column. Then last thing is the K value. So K value is nothing but rate constant or so this should be K1 because we are taking it as K1 only here. So K1 is equal to function of PA into 0.8 divided by T. So the variable is function of PA. Substitute the function of PA value here and a T variable from the first column. So for each f of PA and T variable, we need to find the K1 value. So K1 value here we can get at every data point we get some value for K1 like 0.122, 0.1265, then 12. So all the values are something like a consistent value. We are getting 1, 2, 5 or 1, 2, 3 like that only. So almost all the values are similar values. This means that we are getting a concordant value or consistent value for the rate constant. That means definitely the curve should be a straight line. So the conclusion we can able to arrive based on this by comparing the value of this K, different K values. Now since we have the number of K values available here, let us to take the mean value or average value for the K. That mean value is nothing but we have to find the average value for this K, that is 0.12657. Now rate equation is, so being a first order reaction, so for a first order reaction the rate equation is minus R is equal to minus dP when it is equal to K1 CA. So K1 value is this one. So this one is nothing but K1. So K1 into either in terms of concentration, you can write in terms of minus dCA by dt is equal to K1 CA or in terms of partial pressure also. P also we can use. Since it's a gas phase reaction, it's better to use the variable called as partial pressure. So minus dPA by dt is equal to 0.1265 into PA. So this is the final rate equation which represents the change in concentration or change in partial pressure of component A as the reaction is proceeding. So I request the students to go through this step-by-step procedure. So how to work out the problem, and if any clarification if you have means you can ask me later on. So thank you for watching this lecture.